Hey everybody, it's Ken. We've seen the left-hand approximation. We've seen a little bit about summation notation. Here I want to show you two more ways to approximate the signed area under a curve. I'm going to use the midpoint approximation and the right-hand endpoint approximation. I'll also show you an example of putting midpoint approximation into practice. So first of all, let's just write down those formulas. So now that we've got summation notation, I can actually write them down pretty quickly. I'll include the left-hand formula just for your reference. This is the sum from I goes from 0 to n minus 1 of f of x sub I times delta x. Delta x in all of this was always the common width of all the subintervals, b minus a over n. So you've got an interval from a to b. Say you had some function, and you've got interval from a to b. You've got a function defined on that interval. It looks like that, and you're chopping it up into equal subintervals, each of width delta x, and then you're using left-hand endpoints to get those heights for the rectangles. You can see me picking off like the left-hand endpoint of each one. And actually downstairs you can see that that delta x times f of xi isn't exactly the area of the rectangle, it's the negative because the value of the function is negative. That's why I said signed area at first. What you're approximating is this area minus that area. We call that signed area. And so there you had a formula for the left endpoints. I can write one down for the right endpoints. What you would be doing in your approximation instead is nothing but taking the value of the right endpoint, which would be up here instead of left endpoint over there. And to write that down in notation, you'd just say f of x I plus 1, because to get to the next endpoint, you just add 1 to the subscript times delta x. So these formulas look very similar, but they give you slightly different approximations. If here's x0, x1, x2, x3, so on the first interval, instead of f of x0, you've got f of x1. You'd be up here. That'd be a little bit different rectangle. And what about the midpoint approximation? We use m for midpoint with n rectangles. What that's going to be is you want to use the midpoint of your ith subinterval in order to capture the height for your approximating rectangle. Draw a little bit of a picture here. So if your ith rectangle has left endpoint xi minus 1, right endpoint xi, you want to look at the midpoint. We call that xi bar. And then you want to take the y value of that. So the midpoint of these two is just the average of xi minus 1 and xi. So that's just going to be xi plus xi minus 1 over 2. That's just the midpoint formula. And then to find the midpoint approximation, you're adding up rectangles where the y value is now coming from the center of each one. So again, it's just your y value giving you f of the midpoint times the common width. And I, in this case, is going to go from 1 to n. So for instance, when I is equal to 1, you've got the first subinterval going from x0 to x1. And then your midpoint is just this x0 plus x1 over 2. So those are the three basic area approximation formulas. There are others, but those are the ones that are most famous. And what can I do now? I'll show you an example of how to compute the midpoint approximation. Let's see that. So let's take f of x equals natural log of x. And let's take our interval from a to b to be interval from 1 to 3. 1 to 3. And let's use 5 subintervals. So how can we calculate this? One way to calculate this is to try to struggle through this formula and plug everything in, but I like to just sort of reason it out for simpler examples like these when you know you just have a smaller number of endpoints. Yes, the formula is true, but it's good to kind of just use our own reasoning. So for instance, how do I figure out delta x? So delta x, I know that's going to be b minus a over n, so delta x in this case is going to be, so b minus a over 5 is going to be 3 minus 1 over 5. That's 2/5, that's 0.4. So then what are these midpoints going to be? Let's try to figure it out. I'll come down here. So our x0, that's our right-hand endpoint. That's 1. And then I've got x1 has to be 1.4, 1 plus 2/5. So on and so forth. x2 is 1.8. x3 is, add 0.4 to it, get 2.4. Running out of space, but x4 is going to be 2.6, and x5 will be the number 3, of course. So what about these x1 bars? So it's the average. It's the middle between 1 and 1.4. So x1 bar has to be 1.2, and x2 bar has to be the average of 1.4 and 1.8. It has to be 1.6. So you see, I don't really need to use the formula. I can just sort of reason it out just by finding delta x and using what I know. And once you've got the first average, you can see it's just increasing by delta x each time. It's just increasing by 0.4. So x3 bar equals 1.6 plus 0.4. That's going to be 2. x4 bar will be 2.4. And finally, x5 bar is going to be 2.8. So those are the x values that are going to allow me to plug into natural log of x to get my y values. So when I finally do all of that, I'm just going to get, well, I have to multiply by delta x, the common width. I have 0.4 times. It's going to be natural log of 1.2 plus natural log of 1.6 plus natural log of 2 and plus natural log of 2.4 plus natural log 2.8. All of that multiplied by 0.4. So you see I've got 5 rectangles, 5 numbers, base times height, base times height, base times height, base times height, so on and so forth. All of that's going to equal roughly 1.3. I'll leave it to you to plug it into your calculator and do the multiplication. I did it as well, and that's the answer that I got. What I will do is I want to show you a picture now of what I've done. I'll show you the picture of the actual approximating rectangles, the areas of which we've calculated. So there it is. And so you can see that's the function natural log of x. You can see those 5 rectangles, and right where they're hitting the y value, that's, if you walk downstairs, you'll see each one of these, each one of those midpoints.